For our first real lecture of the term, let's go ahead and talk about angles. We should be able to measure angles using the most common units of measurement, which are degrees and what are called radians. We should be able to convert between those two common ways of measuring angles, convert between degrees and radians. We should be able to relate angles to directions in the xy plane, and we should be able to determine whether or not two angles are what is called coterminal, meaning that they point in the same direction. So what is an angle? An angle is simply a way of measuring an amount of turning or rotation. And there are several different common uses for angles, one of which, for example, is to describe the shape of a triangle. You might have one triangle shaped roughly speaking like this, and we would describe its shape by describing the amount of turning between leg number 1 and leg number 2, the amount of turning that you would need to turn from leg number 2 to leg number 3, and the amount of turning that you would need to do to move from leg number 3 back to leg number 1. Angles are also used to represent objects that are moving in a circle or objects that are rotating or spinning. For example, suppose that you have an object that's moving along a circular track, and you have an observer standing in the center who is looking at this object as it's moving. The movement of the object can be described in terms of the angle of the observer. For example, how fast is this object moving around the circular track can be described by how fast is this observer in the center of the circle having to spin around in order to keep their sights on the object or person moving on the track. And finally, the last application of angles that we're going to be interested in is to describe directions. You can say, okay, I'm going to call one direction angle 0. And any other direction can be specified by saying start looking here and turn by a certain amount described by an angle, and now you're looking in the direction that I'm thinking of. Now when we're measuring or describing an angle to someone, there are 3 common units that we use to describe it. When I talk about units, let's go back to length for a minute. There are lots of different common units for length depending on what country you live in and what kind of thing that you're describing. If you live in the United States and you're describing something that's relatively small, you might describe length using units like inches. If you live outside of the US and are describing something small, you might describe it in terms of centimeters. Like with length, there are lots of different units that are used to measure angles, which are appropriate in different situations. The first way to measure angles is as a fraction or as a multiple of a full rotation. So I could say something like 1/4 of a rotation. This would be an amount of turning that corresponds to going 1/4 of what it would take to go all the way around. So that would correspond to the angle which is specified here in white. Or I could say something like 2 rotations, which, as the name would suggest, would correspond to spinning around twice. That amount of turning. Now, more common than that, and sometimes more convenient, is to specify an angle using degrees. The definition of a degree is that there are 360 degrees in one full rotation. And degrees are denoted by putting a little superscript circle on top of the number. This is the degrees symbol. So if I said something, for example, like 45 degrees, 45 degrees is equal to 360 divided by 8. So this would be equal to 1/8 of a rotation. So how would I draw this amount of turning? Well, I would take that quarter of a rotation from the previous example and I would cut that in half, and I would be moving through an angle that looks something like this. Now, the last traditional way of measuring an angle is to use something called a radian. And radians satisfy the property that there are 2 times pi radians in a single rotation. So in other words, 2 pi radians corresponds to 360 degrees. So for example, if I wanted to figure out what amount of turning corresponded to, for example, just pi radians, well, if 2 pi radians is a full rotation, then a single pi must correspond to half a rotation, or half of 360 degrees, which is 180 degrees, which corresponds to turning all the way around. If I wanted to figure out what corresponded to pi over 2 radians, then I could take that pi radians and cut all of that in half, and so half a rotation would become a quarter of a rotation, and 180 degrees would cut in half and become 90 degrees. So this is this so-called right angle again. Now be warned, if you ever see an angle that doesn't have its units explicitly stated, that angle is always understood to be given in units of radians. So for example, if someone says an angle of pi divided by 4, then we need to understand that because pi over 4 doesn't have any explicitly stated units next to it, that this is going to be pi over 4 radians. If somebody says an angle of 1 with no explicitly stated units next to it, once again, this is understood to be 1 radian. The only time that you know for sure that you're working with something in degrees is if you have something with that little degrees circle next to it. For example, if you see something like pi divided by 3 with a circle next to it, that degree circle says this is pi over 3 degrees. But if you see something like 90 with no degrees circle, this is 90 radians. So please be careful as you're writing your work, and as I'm grading it, I am absolutely going to be literally interpreting everything that you write. If you write something without a degrees circle, I'm going to say they mean radians. And if you write something with a degrees circle, I'm going to say they mean degrees. Now if I take this equation in green and I divide both sides by 180 degrees, then I get the fact that if I take pi radians and divide it by 180 degrees, I get the number 1. And 1 is a very special number because if you multiply something by 1, then the object's value doesn't actually change. So suppose that I had an angle in degrees and I wanted to change it into an angle in radians without actually altering the value and changing the amount of the angle. Then I can do that by multiplying by 1, but by multiplying by 1 in such a format, 180 degrees with pi radians on the top. By doing this, I can cross-cancel the degrees, and now I get angle times pi divided by 180 in radians only. So if you want to convert an angle from degrees to radians, take the angle, divide it by 180, multiply it by pi, and that will be the angle in radians. Now scrolling back up, instead of dividing by 180 degrees, I could alternatively divide by pi radians and make that appear in the denominator of the fraction. So now I get 1 in a slightly different format, 180 degrees divided by pi radians. Because I have radians in the denominator of this fraction, I can use it to cancel out radians if I multiply. So in other words, if I have an angle in radians, and I multiply it by this version of 1, which has pi radians in the denominator, and 180 degrees in the numerator, now the radians will cancel out, and I'm left with units of degrees only, angle, my original angle, multiplied by the 180 in the numerator, divided by pi. This would be the angle in units of degrees this time. So if you want to convert from an angle in radians to an angle in degrees, multiply the angle by 180, divide it by pi, and this will be your angle in degrees. Let me give you two of those really common angles. The first really common angle that we will be working with in this class is the angle 45 degrees. So let's use that conversion formula to figure out what that would be in radians instead. So I currently have an angle in degrees. So I'm going to multiply it by the fraction that has the degrees in the denominator, 180 degrees in the denominator, and which has pi radians in the numerator. Now I'm just going to write pi because remember, when we write an angle with no units specified, radians is always understood. So if I write an angle of just pi, you and I will both understand that that means pi radians. So the degrees in the numerator on the left cross-cancel with the degrees in the denominator on the right, and I'm left with 45 times pi over 180 degrees. Now it's possible to reduce this fraction because 45 goes into 180 4 times in total. So 45 degrees is equivalent to the number pi over 4 in radians. Next, let's work on another really common angle for our purposes, the angle pi over 6. Now because the angle's units are not specified, we understand pi over 6 to be in the units of radians. So what I'm going to do is I'm going to take that pi over 6, which is understood to be in units of radians, and I'm going to multiply it by the fraction that has radians in the denominator so that I can cancel out those units. So 180 degrees in the numerator. So now not only can I cross-cancel radians, but I can also cross-cancel this pi, which shows up in one numerator and one denominator. So that leaves me with 180 over 6. Now 6 goes into 180 30 times, so pi over 6 radians is equivalent to 30 degrees. So in other words, if you take pi radians, which is the same thing as 180 degrees, and divide it by 6, then you get 30 degrees. Alright, let's go ahead and convert the angle 1. So 1 radian, maybe rad for short, I'm going to multiply this by the version of 1 that has radians in the denominator so that I can cancel it out. Now I'll put 180 degrees in the numerator. So 1 radian is equivalent to 180 divided by pi degrees. Now this as an answer is perfectly valid, but it's not particularly meaningful right now. I'm having big trouble envisioning what this angle looks like in my mind. So let's go ahead and find a decimal approximation for 180 divided by pi. So off on the side, I busted out my calculator, found a decimal approximation for 180 divided by pi, and this works out to be approximately 57.3 degrees. So visualizing this is a little bit larger than 45, which is perfectly diagonal. This is quite a bit smaller than 90 degrees, which would be this right angle. So it's going to be, roughly speaking, maybe around here in terms of visualization. This would be 1 radian. Now, angles can be used to specify directions specifically in the XY plane. And when we use angles to specify directions in the XY plane, we do it in the following way. First of all, you, the observer, should position yourself at the origin, the location where the X and Y axis intersect. This is usually represented by 0, 0 in coordinates. And start facing the positive x-axis. Start facing to your right. Now someone comes to you and they say, all right, here is an angle. And depending on whether the angle they tell you is positive or negative, you're going to turn a certain amount in a certain direction. If the angle is positive, you need to turn counterclockwise, which would be toward the positive y-axis, by the amount specified by the angle. If the angle is negative though, that's a sign that you need to turn clockwise, which is toward the negative y-axis. For example, let's get some exercise drawing angles in the xy plane to show that the direction that they indicate in the xy plane. Let's start with 90 degrees. It's definitely degrees because you can see the degrees circle written above the number. So 90 degrees would be equivalent to 1/4 of a rotation. It would be equivalent to pi divided by 2 radians. So I'm going to draw the xy plane. Here's x horizontal and here's y vertical. And I'm going to start by positioning myself at the origin and looking over to the right in the direction of positive x. Now 90 degrees is a positive angle, so I'm going to turn counterclockwise. I'm going to turn toward the positive y-axis. And so I'm going to turn 1/4 of a rotation, which will point me straight upward. So this angle right here would be the angle 90 degrees, and the corresponding direction would be straight up in the direction of positive y. degrees. A 45-degree angle is corresponding to a rotation of 1/8 of a full rotation, and is also equivalent to pi divided by 4 radians. Let's see what this angle looks like in the xy plane and what direction it's pointing toward. So I'm going to start by looking to the positive x direction, and then I'm going to turn 1/8 of a rotation, and I'm going to turn counterclockwise because the angle is positive. So that will position me right around here. The angle, 45 degrees, is the amount of turning that it took me to go from positive x to this green direction, and the green arrow itself is the corresponding direction to an angle of 45 degrees. Alright, what about the angle 3 pi over 2? Once again, no degrees symbol, so this is going to be in units of radians. In the beginning, it can be a little bit hard to visualize the angle that you're working with, because radians are not as common a unit of measurement in day-to-day life. So you may find it easier to convert this angle to degrees before you try and draw it. So I'm going to take 3 pi over 2 radians, and I'm going to multiply it by the fraction that has radians in the denominator and has degrees in the numerator. Maybe it'll be easier to understand this angle if it's in degrees. So cross cancel the pi's, cross cancel the common factor of 2, and I get 3 times 90 degrees, I get 270 degrees. So I'm going to go to my xy plane, and I'm going to start facing in the positive x direction, and then I'm going to go 90 degrees counterclockwise 3 times. 90, 90, and then another 90, which gives me 270. So this angle here, this amount of turning is 270 degrees, and here's the corresponding direction. Okay, let's finally do an exercise with a negative angle. Here we have negative pi over 2. Now negative pi over 2 is equivalent to negative 90 degrees. We've already converted pi over 2 to positive 90. Negative pi over 2 is just negative 90 degrees. So let's go ahead and let's draw this angle. Here I am with the xy plane, starting at the origin, pointing to the right. So this time I'm going to turn by 1/4 of a rotation, but not toward positive y. This time I'm going to turn toward negative y. So here's the corresponding angle, negative 90 degrees, and the direction in which it points is the same direction that we had in part C of this exercise, the direction which points straight down. Now what's interesting about exercises C and D is that even though we had 2 different angles, they corresponded to exactly the same direction. It's just that the way that we got to that direction was different. In my opinion, the easiest way to tell if 2 angles will point in the same direction is to see if there's going to be a full 360-degree rotation between the 2 angles. Two angles corresponding to the same direction are called coterminal. Coterminal, from the root words co, meaning same, and terminal, meaning stopping location. So 2 angles are coterminal if, when you draw them, you end up stopping, pointing in the same direction. For example, let's take 250 degrees and negative 470 degrees. Are these 2 angles coterminal? If you drew them, would they point to exactly the same direction? Now, because drawings are inaccurate and imprecise, it can be difficult to answer this question graphically. So let's go ahead and answer this question with arithmetic, with algebra. Let's subtract the two angles and figure out if there is a multiple of 360 degrees between them. So I'll take 250 degrees and I will subtract negative 470 degrees. 70, which is equal to 720 degrees. Now 720 degrees is equal to 2 copies of 360, which is equal to 2 full rotations. So the two angles are separated by 2 full rotations. And therefore, yes, they would be coterminal. They would end up pointing to the same direction. What about the angles negative pi over 4 and 7 pi over 4? Are these angles coterminal? To figure that out, let's subtract the two and let's figure out whether or not there are full rotations between these angles. So I could, for example, take 7 pi over 4 and subtract negative pi over 4, which is equivalent to 7 pi over 4 plus pi over 4. Now these two fractions have the same denominator, so I can add the two numerators over the common denominator. Now I have 7 pi's plus an additional pi, that's 8 in total. And if I reduce that, I get 2 pi as the difference between these two angles. 2 pi is equivalent to 1 full rotation. So yes, these two angles would be coterminal, because there is a single, in this case, full rotation between them. What about the angles 0 and 5 pi? Now if I subtract these two, then I get 5 pi. But 5 pi is not a multiple of 2 pi. 2 pi being 1 full rotation in the units of radians. So because these two angles are not separated by full rotations, these two angles would not be coterminal. For our final exercise, let's go ahead and determine the angles that correspond to the following locations on the xy plane. And to begin with, let's figure out what angles would correspond to the positive y-axis. And one way to get to positive y would be to turn counterclockwise by 1/4 of a full rotation, which is equivalent to 90 degrees. But this is just one way to reach the positive y-axis. There are other ways, other angles which are coterminal to 90 degrees. I could go clockwise instead of counterclockwise. And I could go negative 270 degrees. This would be equivalent to taking 90 degrees and removing a multiple of 360, going in the opposite direction by a full rotation. Or I could go 90 degrees and then do a full 360 to get me back to the positive y-axis. So let's see, 90 degrees, if I spun around an additional 360, that would give me 450 degrees in total. There's nothing stopping me from doing 2 360s. For example, I could do 180 degrees, and etc., etc. There are, technically speaking, infinitely many answers to this question, infinitely many angles pointing to positive y, depending on how many times you want to spin 360 degrees, either clockwise or counterclockwise. So 90 degrees is in some sense the most common or the most standard answer to this question, but there are infinitely many other answers. The same thing will be true for these other angles. The negative y-axis, for example, can be reached in a bunch of different ways. Starting from the positive x-axis, one way to reach negative y is to turn clockwise by 90 degrees. So in other words, an angle of negative 90 degrees would correspond to negative y, so on and so forth. Anything that is separated from negative 90 by a full rotation. The negative x-axis. Probably, in my mind, the standard, the first way that occurs to me to reach the negative x-axis is to go 180 degrees in the positive direction counterclockwise. But you could just as easily go 180 degrees clockwise, etc., etc. And for the positive x-axis itself, the easiest way to get to the positive x-axis is to start from the standard direction and just not move at all, which would correspond to an angle of 0 degrees, no turning. But from this position, you could do a full rotation, either in the clockwise direction or in the counterclockwise direction, or you could rotate more than once, etc., etc. That concludes today's material. Today we introduced angles, which are a way of measuring an amount of turning or rotation. Angles have a lot of different uses that we will study in full throughout this class, including describing the shape of triangles, describing a spinning or revolving object, and to describe directions in the xy plane. We studied two commonplace ways to measure angles, degrees and radians, and we studied ways to convert between those measurements. Then we looked at angles in the xy plane and how angles correspond to directions in the xy plane, and we looked at coterminal angles, which are two different angles which point to the same direction.